Give me an R. R. Give me an A. A. Give me a Y. Y. What's that spell? Ray. What's that spell? Ray. What's that spell? Ray. Welcome to Physics with Joe. Today's video is all about ray tracing for concave mirrors. I'm going to talk about what ray tracing is, what are the four principal rays that we use in ray tracing, and then we'll use ray tracing to figure out the different kinds of images that can be produced by a concave mirror. So without further ado, let's jump right into it. What is ray tracing? Simply put, it's a graphical method of determining everything you want to know about an image, which is based upon the law of reflection. Using ray tracing, you can determine the location of an image, so how far away the image is going to be from the mirror, the size of the image, is it going to be enlarged or reduced relative to the object, the orientation of an image, is it upright or inverted, and finally the kind of image, is it going to be a real image or a virtual image. A typical kind of problem that you might use ray tracing for could be a 40 centimeter tall object is placed 150 centimeters away from a concave mirror with a focal length of 50 centimeters. Where is the image located? Is it real or virtual? Is the image upright or inverted? And finally, is it enlarged or reduced? Now let me say that I would never use ray tracing to get a numerical answer. It's kind of like adding vectors graphically using the tail to tip method. What we'll see is that ray tracing is a very valuable way of double checking your results when you solve problems mathematically using the mirror equation and the magnification equation. Let's start with a few basics. Any concave mirror can be considered to be a section of a bigger sphere. And the center of that sphere, of which the concave mirror is a section, is called the center of curvature. The distance between the center of curvature and the middle of the mirror is called the radius of curvature. Parallel light rays coming in will all meet at a single point after reflecting from the concave mirror, and that point is called the focal point. The distance between the focal point and the middle of the mirror is called the focal length. And for a concave mirror, the focal length will be 1/2 the radius of curvature. So the center of curvature is always twice as far away from the mirror as the focal point. And finally, the central axis is just a horizontal line that's drawn passing through the center of curvature and the focal point and the center of the mirror. The way ray tracing works is you draw your central axis and you draw your concave mirror. And then you're going to draw an arrow to represent the object a certain distance away from the mirror. That distance will be dependent upon the problem. You're also going to draw on your central axis a center of curvature and the focal point. And then what you do is you draw the principal rays that I'll get to in a minute coming from the top of the arrow. Where those rays intersect after reflecting from the mirror is going to be where the image is located. Now it's a little bit different if I have a virtual image, but in essence, you draw your arrow representing the object, you draw the principal rays coming from the tip of the arrow, and you look for where those principal rays meet after reflecting from the mirror. The four principal rays are as follows. Ray 1. A ray initially parallel to the central axis after hitting the mirror will reflect through the focal point. Ray 2. A ray passing through the focal point after hitting the concave mirror will reflect parallel to the central axis. Ray 3. A ray traveling along a line passing through the center of curvature after hitting the mirror will reflect back upon itself. And finally, ray 4. A ray hitting the center of the mirror reflects at an equal angle on the opposite side of the central axis. When you're doing ray tracing to figure out the characteristics of an image, you always start by drawing the central axis and the concave mirror. Now, if you were to use ray tracing to try and get a numerical result, then you would draw the focal point, the center of curvature, and the object the correct distances away from the mirror using some kind of scaling factor probably. However, we're just going to use ray tracing to get the general characteristics of the image. Now the object you usually draw as an arrow regardless of whatever the object is, and you always draw the 4 principal rays starting from the top of the arrow. And what you're looking for is where do these 4 principal rays intersect. The point where they intersect is going to be the image location. So ray 1, if you recall, is a ray coming in parallel to the central axis after hitting the mirror will reflect through the focal point. Ray 2 is kind of the opposite of that one. A ray passing through the focal point after hitting the concave mirror will reflect parallel to the central axis. Ray 3, a ray traveling along a line passing through the center of curvature after hitting the mirror will reflect back upon itself. And then finally ray 4, a ray that hits the center of the mirror will reflect at an equal angle on the opposite side of the central axis. What you're looking for is where do these 4 rays meet. That will show you where the image is going to be. So I could get the image location by looking at how far that image is from the mirror. I could figure out the image height by actually measuring the height of that and using some kind of scaling factor and so on. But for us, the important thing I want you to notice is that the image is inverted relative to the object. The image is smaller than the object. And since all 4 light rays are actually meeting at a given point, the image is a real image. So one of the things we'll see in a second is anytime I have an object which is beyond the center of curvature, that is always going to produce a real image. That real image is going to be located, let me pause this for a second. That real image is going to be located between the center of curvature and the focal point. It's going to be a real image which is reduced in size and inverted relative to the object. So let's take a look at the different kinds of images that can be produced by a concave mirror. Now let's use ray tracing to investigate the different kinds of images that can be produced by a concave mirror depending upon how far the object is from the mirror. 2 quick points. 1, this simulation is only showing 3 of the principal rays. It's not showing principal ray 3. A ray passing through the center of curvature is going to reflect back upon itself after hitting the mirror. But it doesn't really matter because, like I said, all you really need to do is draw 2 of the principal rays and see where they intersect. Second thing is the focal point is this very first point marked on the simulation. The center of curvature is this second point, and the center of curvature is always going to be twice as far away from the mirror as the focal point for a concave mirror. Now, anytime the object is beyond the center of curvature, so the object distance is bigger than the radius of curvature, I'm always going to get a real image. You can see these 3 points, these 3 rays are meeting at a given point after reflecting from the mirror, indicating that we have a real image. That real image is always going to be smaller than the object, so it's going to be reduced. It's going to be inverted relative to the object. So for an object beyond the center of curvature, we're going to get a real image which is reduced in size and inverted, and that image is always going to be between the center of curvature and the focal point. If I'm at the center of curvature, then the image is also going to be at the center of curvature, and it's going to be the exact same size as the object except flipped upside down. If the object is in between the center of curvature and the focal point, the kind of image I'm going to get is going to be a real image because the 3 rays are meeting at a given point after reflection. That image is going to be inverted relative to the object, and in this case it's going to be enlarged. So for an object between the center of curvature and the focal point, the image is real, enlarged, and inverted relative to the object. And if we have the object at the focal point, what ends up happening is after reflecting from the mirror, these light rays never meet and they don't look like they originated from a point. I actually do not get an image when I have the object at the focal point. Technically, the image distance is infinity. And then if I am in front of the focal point, then what I get, let me decrease this height a bit, is the 3 rays after reflecting from the concave mirror do not meet at a single point. However, if I trace those rays backwards, they look like they originated from a point behind the mirror. This is a virtual image. So anytime I have the object in front of the focal point, I'm going to get a virtual image. That virtual image is going to be behind the mirror, and it's going to be enlarged. So the image is going to be bigger than the object, and it's going to be upright. So for an object in front of the focal point, we get a virtual image, which is enlarged and upright and behind the mirror. In summary, if the object is beyond the center of curvature, the image is going to be a real image, which is going to be inverted relative to the object and is going to be reduced in size. If the object is between the center of curvature and the focal point, again, we're going to get a real image, which is inverted relative to the object, but in this case, the image is going to be enlarged. It's going to be taller than the object. And then finally, if the object is in front of the focal point, we're going to get a virtual image, which is going to be upright relative to the object, and it's going to be enlarged. The virtual image will be taller than the object. Well, that is it for ray tracing for a concave mirror. In my next video, I will do ray tracing for a convex mirror, which you'll see is much simpler since convex mirrors can only produce one kind of image. Until then, my name is Joe McCullough. Thank you so much for joining me for Physics with Joe, and I hope to see you later. So until then, I still need a catchphrase.